right, I've got to introduce Jeff Cotter, who's our speaker today, who many of you know. And actually, Jeff points out that he and I started working together 25 years ago, which is probably before some of you were born. I was a graduate student at the time. I was a graduate teaching assistant. Must have been, right? 25 years?
No, you were my teacher.
That's far back. I just think I was. And Jeff wrote a senior thesis and did a PhD, and he actually was one of the early people at Astropower during some really interesting times. And we made a solar cell at that time, probably in the late 90s, that was 20 centimeters by 60 centimeters. And many of you complained that NREL can't measure solar cells, and they always get the fill factor wrong. They put a probe on it, and it was about 30 amps, and they were kind of surprised at what happened. So we learned how to put big wires on it. Jeff had great sense of humor, which I'm sure he carried over into these days. And we let him write the company newsletter, which extrapolated that solar cell into one that was the same size as the building. Remember that newsletter? I obviously didn't forget it. He also coordinated some rather large proposals in the millions of dollars, which were, I think, all successful. And after I would review where they were headed with the proposal and the budget, I was done. And he would then, after they shipped it out, he'd give me a copy. And he kept coming by my office saying, have you looked at the proposal yet? I said, I don't have to look at the proposal, it's done. And finally he turns to the page, the biography page. Remember that, Jeff? And my biography was, we found Alan Barnett walking the halls, so we decided to add his name to the proposal. But Jeff's been a solid contributor. He helped found Spree, as some of you may know. And he and Martin and Stuart and Christiana, and a lot of people who predated Spree as an independent organization. He then got promoted to associate professor and took that opportunity to join SunPower. And where he was for 5 years, and he became quite expert in manufacturing. He's now living in California, and he's collaborating with ASU and Arizona State University, if you don't know, and ANU. And Allison's trying to get him to teach a course here, which maybe he will do next winter, next summer.
Summer of 2015.
Our summer, their winter, all the above. So, Jeff, come get it.
Okay, thanks, Alan. Thanks for the kind introduction. It's nice to be back. I tell you, it's nice to be back in Sydney and back on campus. And this building is completely new, so it's a lovely building, and it's great to see. There's a lot of vigor and a lot of activity still going on here in solar. And Allison was telling me that the intake now in the undergraduate degree program is around 100 students, and I'm just so happy to hear that. And it just really makes me happy to see that it's, solar is going strong here in UNSW. So it's great. I see a lot of faces that I remember. Hi, Mark. I don't remember everybody's name. Hi, Hamid. And I apologize if I don't remember your name. I'm terrible with names. Matt? Was that Matt? Hi, Matt. Wow. Okay. I had to do a double take. I didn't recognize you. Okay. So it's nice to be back. And today I'm going to talk about a subject that's near and dear to my heart, and that is about engineering in a manufacturing environment. And so when I went to SunPower, I thought I knew everything there was to know about solar cells. I could tell you where every single electron and every single hole was in any particular solar cell. I knew where it was. And I got to SunPower and I had no idea what anybody was talking about. It was just blah, 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 SBC, blah, blah, CPK, blah, blah, lifetime. And so I went super low on the learning curve while I was there, and it was a fantastic experience. I got to see a lot of very, very nice solar cells get made in high volume, and I learned a lot. And then decided that it was important that engineers like yourselves understand how engineers function in a manufacturing environment, so you can contribute in that area as well if you should choose. I'm also trying to enthuse young students to go and take up careers in manufacturing, engineering, and PV because there's so much work to be done still in PV to make this industry take off. So I'm going to touch on 4 topics. I might go a little fast through subject 3 because I have too many examples and I might have to skip a few of them, so I apologize in advance. I'm going to tell you why I think it's important that engineers understand about manufacturing cost and they understand how to do something about it. That's my value proposition. A few slides on how we account for the cost in manufacturing. I think it's an interesting topic, and I think engineers should understand how cost accountants think and how they work because they have a wealth of information that's super valuable in doing engineering work in a manufacturing environment. Then I have made up a fictitious example of a problem in a factory, and I'm going to explain to you some of the steps that we take as engineers in order to tackle the cost associated with these problems. How we do it, what skills we have. You're going to see a smorgasbord of skills and topics that I want you to get a sense for, but not necessarily learn them in detail. And if you do take an interest in this topic, I'll tell you a little bit about the course that I'm developing in collaboration with University of Delaware, Arizona State, and Australian National University on the science of manufacturing of solar cells. But before I do, I have some good news, some happy news. I got married. Many of you know Florence Chen. She was a student here, and about 4 weeks ago, we tied the knot in California. And then last weekend, we did it again in Hong Kong. So we are now officially married. So that's good. Okay, let me start with my value proposition. Why is manufacturing cost so important? When I say manufacturing cost, I mean cost of goods manufactured, which I'm going to abbreviate to COGM, cost of goods manufactured. Why is it important? It's important because you can attack the cost of your manufactured products. The first benefit you get back from that is immediately that contributes to your bottom line. It contributes to your cash flow. So your cash flow is your revenue and minus your cost of goods manufactured. So if you can take a penny a watt out of your cost of goods manufactured, then that goes right into your pocket. So that's good. That's cash flow. And cash is king. When you have cash in the business world, you can grow your company faster than the other guys. You can invest in R&D. You can suffer better, weather the times when price pressure is on your margins, and so forth. So cost of goods manufactured contributes directly to your cash flow. Now, one thing that you have to keep in mind is that when you make improvements to your manufacturing cost, any given project that you might undertake has a relatively small impact in terms of dollars per watt. And people who are in the research area and the development area kind of don't get very excited about this when I say we can take 0.5% of end-of-line yield out of our cost, and it'll be 1/4 of a penny, 1/4 or 1/10 of a penny in terms of dollars per watt. They just look at me like, well, so what? But if you think about it, when you're manufacturing and you have a very large manufacturing base, often these small improvements can be globalized to the whole manufacturing base. So if you're at a gigawatt, and you can take 1/4 of a penny out of your cost of goods manufactured, that has a 5-year net present value of something like around $10 million. $10 million, right? So you can afford to do a lot of engineering work on relatively small problems for $10 million worth of project funding. And often you can do these projects for less than $1 million or something, so you end up with a very, very good return on your investment by attacking these small problems in manufacturing. Another thing to keep in mind too is that manufacturing is such a broad and complex operation. There are many, many opportunities to tackle these kinds of cost of goods manufactured improvements. Many of them, and especially when you consider the whole span of the PV value stream, from refining silicon through wafering, through cell, through module, through systems, there are a lot of opportunities for you to go and tackle improvements. They're small, but if you leverage them across the manufacturing base, they can be lots of money in your pocket. So here's my example. Imagine you have gap to entitlement. So that means that your cost is 50 cents more expensive per watt than what you can do at entitlement, right? Entitlement is kind of the best possible cost you can ever get. maybe it's tied somehow to the embodied energy of your product, right? So labor is free, capital is free. You got 50 cents of an opportunity there. If you can do 5% of that, if you can pull 5% of that year on year, and that's a very, very conservative number, but if you can pull 5% of that out year on year over 5 years, that's 11 cents per watt peak that you can gain in 5 years' time. And that's not a small number in PV industry. 11 cents per watt is a pretty big number when you talk about, pushing the, below $1 per watt, below 70 cents per watt, approaching 50 cents per watt prices in the next 5 to 10 years. So it can be quite significant if you're focused on it and you're good at it. The other thing too is in a factory environment, you usually have pretty big and pretty well organized engineering teams, and they can run lots of projects concurrently, right? They can do some projects on the metallization area, some projects in the diffusion area, some projects in the wafering area. You can sort of work concurrently on multiple projects in parallel. And so if you do 10 small projects a year that are successful at 1/4 cent per watt, then that's 2.5 cents a watt you can pull out of your cost of goods manufactured every year. 2.5 cents, that's $100 million in 5-year NPV. All right. The other thing that's beneficial too is that when you do these kinds of goods manufactured cost improvements, they can be done on a very short time frame, relatively very short time frame. So especially when you compare them to projects where you're developing a new technology platform or you're making a major improvement to an existing technology platform. So for example, new technology platform developments take on the order of 10 to 20 years, right? So maybe you've seen the new graphene solar cell from MIT, right? So they have a little square millimeter of graphene. They use sticky tape to make it. They put in the, right? They're 20 years away from having any impact on the price of PV, the cost of PV. And then there are a lot of really good platform improvements. Like a good example is the Pluto cell technology that was developed at Suntech and here at UNSW, right? That kind of platform improvement is still based on silicon, but that kind of project takes in the 1 to 5 years of time frame before you can have an impact on your cost. And then all these little tiny cost of goods manufactured improvement projects can be done in 1 to 5 quarters, roughly 1 to 5 quarters, right? So you can get your impact in a very short period of time, relatively speaking, by focusing on developing your cost of goods manufactured. All right, so I think it's important. And I'm going to try to convince you guys today that this is something that's really important and valuable for the PV industry to focus on in some way in the future. Maybe not as a research activity here at this research institute, but maybe as a teaching and learning activity in the teaching curriculum. We need more engineers who are trained up to do this kind of work. It's compelling, and I think we have a vital role to play in collaboration with our cost accountant counterparts. So I'm going to say cost and cost accountants. The cost accountants are the folks that own the business of accounting for this cost of goods manufacturing. They are the bean counters that spend all their time adding up all the numbers, and it's the engineers who are responsible for doing something about it. So this is your role right here, PV engineers, improve the cost of goods manufactured. So we need you guys to be well equipped as engineers or even as managers. When you're managing an engineering team, it's important to be well equipped with the right skills and knowledge in order to get this job done right and get it done fast. I should back up to my thesis. I had a further thought. This list, the other thing too that's important from a teaching and learning point of view, the skills that you need in order to tackle all these problems and capture this benefit are generic. They're not specific to any given technology. So if you have an interest in thin films, what you need to know about tackling the cost of goods manufactured is the same as if you are working on 3rd gen solar or graphene solar or nano solar or dye-sensitized solar. It doesn't matter. They're all generic skills. So it's good to have them no matter where you might end up. Okay. Good. I'm just going to check my time. All right, we're doing good for time. Now I want to tell you a little bit about how we account for the cost of goods manufactured. It's a topic that I think is interesting, and I want to kind of whet your appetite so you can see how engineers and how accountants think about the costs of the products that we make. And then I'll try to explain to you why I think it's important that you understand this as an engineer. So I took a self-paced course on accounting recently and struggled through accounting, and it's an interesting subject. And I've boiled it down to this is how cost accounting works in a factory, a block diagram. So this is the work in process inventory. That's our factory. It's got all our processing steps. These are totally fictitious, by the way. There's no specific technology here. And what we do is we start here with customer orders on one side, and they have a net accumulated cost at the beginning of $0, zero. So they're just order sheets from a customer. And then they go through the factory, and as we transform them slowly from an order into a finished product, we have to incur some costs in the manufacturing. We need wafers, we need screen print paste, we need sodium hydroxide, we need silane, electricity, we need to pay the building rent, we need to pay depreciation. There's a whole very, very long list of things that we need to bring together in order to transform customer orders into finished products, and all of those things have a cost associated with them. So we account for them. We say, all right, here's all the raw materials, here's all the direct and indirect labor, all the factory overhead. We have some beginning inventory, we have some ending inventory, we have some spoilage and so forth in between. And then once we can account for all of these, we can compute the cost of goods manufactured. It's just the beginning inventory minus the inventory, ending inventory, and then the sum of all the cost contributors. So raw materials plus direct and indirect labor plus this, plus this minus that. So it's just a sum, a summation, and that becomes our cost of goods manufactured. Here. I added in here, I like to add this in here. It doesn't often get accounted for, but I think it's important. This is this cost of poor quality and reliability. The cost of poor quality and reliability. So if we make poor quality solar cells, we make them, we test them, and we let them go to the customers, and the customers are not happy with them because they don't meet the specification, right? Maybe they don't have the right fill factor or something, and they send them back to us. So that comes back to us. There's a certain cost associated with that, and we have to account for that cost as well. It adds on to our cost of goods manufactured. Okay, so this is how engineers think about cost of goods manufactured in terms of block diagrams. I'm going to use a couple of these block diagrams as we go through some of the examples in the latter half of this presentation. Cost accountants use this really cool concept called the product cost object. And so what they do is they define an object. It's kind of a conceptual thing, and it's called, in our case, it's called the solar cell. And we start out with a product cost object here. We have 2,400 of them each day, and they have an accumulated value of $0. And the product cost objects get transported through the factory, and as they go, they accumulate all of the costs. So after they get the wafer added, they've accumulated $2 in cost per unit. And then after etching, they've now accumulated an additional 15 cents, and so on. So these product cost objects accumulate all the costs, and then they come out the other end, and this fully accumulated cost here, which represents the sum of all the costs as it moves through the factory, this is also the cost of goods manufactured. This one here minus this one here, we start out at 0. So that's the other way we account for the cost of goods manufactured. We do it by product cost objects. Accountants do cost in terms of period cost. So they do dollars per quarter. That's the way they think about it. They think about it in period costs. So all accounting textbooks and all cost accounting work that you'll see is done in terms of a period cost. And we engineers in PV, we like to think in terms of other types of costs. We like to think of the unit cost. So that's just the cost of goods manufactured divided by the number of good product that we make. So, and then we'd like the performance cost too. That's a very well-known metric throughout PV. That's the dollars per watt. So we can convert to dollars per watt just by dividing by the number of good watts that we produce as well. Okay. This is how the whole picture looks if you're a cost accountant. So this is the engineering viewpoint here, block diagram. And this is what accountants work with. So if you're an engineer working and you're trying to get your head around cost, you're not going to get a block diagram. What you're going to get is a T account like this. So this is a typical T account that you get. This is for work in process control for one accounting period. In this case, it's a simulated account. It's for 1 day of production. 1 day of production. So you need to know how to read this type of account statement so that you can see what was the cost of my paste. Last day it was this many grams at that many dollars. That's for one day. Okay, this big bucket approach, this is the big bucket approach to cost. This is the all-in cost for products. Not really super useful for doing engineering work. It doesn't have enough granularity or enough resolution for you to be able to detect what's happening at a level of your particular production line, your particular factory, or your particular processing step that you're responsible for. It's just one big bucket with all the costs kind of lumped in, and so you don't get good visibility on what's happening at, say, for example, if you're the process engineer and you're responsible for this particular process step, you don't get any visibility there. So what we do is we take the product cost object model and we break it down by step. So we can make a product cost object model for one process step. This is for testing and sorting. And so it has the same kind of cost of goods manufactured, which we call the step cost of goods manufactured. We got some partially completed cells. They're from the isolation step. They've already accumulated $10,302 of cost. We add our raw materials. So this is things like compressed dry air, maybe testing pins, maybe lamps for testing, labor, overhead. We've got a beginning inventory, an ending inventory, and then we have all of our yield and poor quality also lumped in here as well. And what comes out the other end is sort of less partially completed cells. They've now accumulated some cost, all of these costs. So that difference there, 10,682 minus 10,302 is the step cost of goods manufactured of $379.60. And we do that for each process step. And then what we do is we assign responsibility for this cost to the engineers who are responsible for that process. We assign them accountability, responsibility, visibility, and we make them accountable for that. So then the engineers, this are testing, sorting engineers, you guys see this every day and people ask you about it all the time, and your thoughts are always on, what are we going to do to get this number down? Because if we don't get it down according to the plan, then Jeff's going to come around and wonder what's happening. He's going to make us do reports and make us write reports and come and report and explain. And so we're very motivated and very focused. I also put on here, this is going to be our example in the next section. I'm going to talk about, this is our example. We'll talk about some things, how we do it. So we have also electrical yield problem here. So six wafers lost, and that's a cost of $27. We got some poor quality wafers due to a local thermal anomaly from the wafer team, from the module team that were returned to us. And then we had poor reliability. We had 6 wafers come back at a cost of $82. That came from the field. Out in the field, there were some modules that had local thermal anomaly. The customer was unhappy. They called us on our warranty. They sent it back, and we ate that cost there. And that ends up in our cost of goods manufactured for this particular step. Okay, so this is kind of the process engineer's point of view. If you go talk to the cost accountants, they have an account just like this. It's a smaller one, and this account is specifically describing what's going on at this particular processing step. And we can use the product cost object model to work our cost of goods manufactured. It's just the net cost of the goods we produce minus the net cost of the goods we acquired, and that gives us our cost of goods manufactured for one step. And we can translate as well. If we want to know per watt or per unit, we can just divide by the total number of good watts and the total number of good units produced by the factory. Okay, so now we have that system. We have it. The cost accountants have set it up. The engineers understand it. They can go and they can read it. They read it like they read how to solve partial differential equations, how a solar cell works. They can derive it from scratch. They all understand about cost. And the managers understand it too, and now we can start to do some useful things with our cost data. So I just wanted to do a couple quick obvious ones. One of the ones that we like to do is we do historical monitoring, right? So we monitor, this is for F-print, front print. This is their step COGS per quarter, and every quarter they're doing good, they're making improvements. They've got a good learning rate, it looks a little exponential, but then what happened here, right? Something happened, they stopped getting better. And so now the managers all spring into action. They're stuck. They need help. So let's just get the R&D team over here and see what they can do to help these guys. Let's hire some new talent. Let's change our direction. Let's do a white sheet of paper exercise and see what other directions we can go in. Another good thing, once you understand how to compute and account for your cost, you can start to do projections and predictions, right? So I've done a projection here based on a learning curve. We're doing 5% year on year, or 5% quarter on quarter, so we expect to see keep going down. And then this step right here, we predict a step reduction in our cost of goods manufactured because we're going to do a tool upgrade. And we understand the cost and we know what the tool's going to fix. We compute exactly how much impact it's going to have on our cost of goods manufactured. So we predict and we project. The other thing we do with cost is we validate, right? So after we've made this prediction, we go and we buy all the upgrades. We go to the factory. We spend 3 days doing the upgrades. And then the next quarter we measure it and we didn't get what we wanted to. So our validation has failed. Okay, so that's important, right? That's important because now we have to go back and we have to spend some time understanding why it was that what we thought was going to work, why it did not work. And so we use this very Inquisition-like process called 5 why nots. And we say, why not did you get your benefit? And then you say, because the upgrade didn't work. And then I say, why not the upgrade didn't work? And you say, because the voltage is wrong. Why not was the voltage right? And we keep doing that until you get right down to the exact problem that describes why we missed. Then we've learned something, we go back and we make sure we get it right. So that's validation, very important. Another good use of understanding cost is benchmarking. So this is a little bit of a busy graph. This is the step COGM for F-print, historically by production line. So that blue one's line 1, line 2, the green one's line 3. And we do it for all the quarters up to now. And then we take a look at that and we say, wow, there's some interesting data here. One of them is we can benchmark against the best known practice. So it looks like the purple production line, line 4, has the best known practice. They're doing something right. That production line is doing something right. Those operators or those engineers have got something worked out that the rest of the factory hasn't figured out yet. So let's go and figure out what that is. Let's figure out what it is. And let's apply it to all the production lines so that we can get everybody down to best known practice. If you're lucky, you can get competitive benchmark data, right? If you can sort it out, you can sometimes extract it from, I don't know, various publications and various financial accounting statements and so forth. You can get a competitive benchmark, and then you can look at where you are against the what your competitors are doing, and you can say they are kicking our backside here. Let's figure out what they're doing, and let's get down to this red line. There's an opportunity here. Let's capture it. And you can do entitlement benchmarking as well. You can work out, like, if we could get down to the embodied energy of the materials that we're using in our process, we could get a cost here, right? So let's figure out why we're not at the entitlement cost. Are we not using our materials efficiently? Do we need to change the reaction chemistry of our etching process? Whatever, you have to go now that you know that there's an opportunity here. You go and you start to work very hard to dissect the problem and figure out why you haven't reached entitlement yet. Okay, so that's another important thing. So just knowing about the cost gives you a lot of visibility when you carry out your engineering work. The first 3 I mentioned already. The 4th one I haven't talked about. You can use your cost data to start to do road mapping or project prioritization. You look for the projects that have the most potential impact to your cost with the least required effort, right? And you put those at the beginning, this quarter, and then you look at the medium ones with medium impact, and you do those next year, and you look at the hard ones with long range projects with smaller impacts, and you start those now at a low level with 1 engineer part-time, and you expect to capitalize on those benefits, say, in the 2 to 3 year time frame. You map it all the way out. You can map it all the way out. You can map your cost structure all the way out into the future, and then you can use that for doing a lot of great stuff in terms of planning and prioritization. Another thing that I found very, very useful in my work is when you can speak about the cost benefits, the project benefits, then you can make a compelling argument within the business to your peer organizations, to your managers, and you can convince them that what you're doing is important, and you can convince them of what the benefit will be. And now you get them on your side, so they will support you, they will provide you with resources. You know, if it's the operations team, if you convince them what you're doing is going to help them, then they will give you extra time on the production line. They'll give it to you during normal working hours. They won't schedule it when they're doing their preventive maintenance, which is a trick they like to use to avoid having to give you any real line time. They will help you. So knowing and speaking and convincing people is good for the success of your work in the factory. As far as engineers go, here are the two benefits. They don't seem like benefits to engineers, but they really are. When you can account for the cost, you can give accountability, visibility, and feedback to the engineering teams. So when there is a problem, they get the spotlight. Okay? And then my favorite expression is it's the application of pain and suffering in the right places to the right time. Pain and suffering. Torture. It's like torture. It's not really torture. It's like torture. You guys, you're the team with the problem, print. What happens is you get the phone calls at 4 o'clock in the morning when something's wrong, right? Your phone rings, so you have to wake up, come to work. Every morning, you get to make a presentation to the operations team. Tell them exactly what you did yesterday in great detail, right? Because they want you to get this problem fixed. You get to tell them exactly what you're going to do in the next 24 hours, right? You guys are on the showcase. And so you feel the pain and suffering. You are very, very visible, and everybody's looking at you, looking to you to solve the problem. All right. So that's, this is tongue-in-cheek, by the way, so don't take this too literally. It feels like pain and suffering, but it's good for you. Okay. Trust me. When it goes away, when the pain and suffering goes away, it feels really good. Okay, so it's good to have a good understanding of this. I wanted to give you some appreciation of it now. I don't have time to spend. There's Gavin. Hey, Gavin. I don't have a lot of time to spend in a lecture, but I want you to sort of to believe me when I say it's important that you know how to talk, how to breathe, how to understand cost. Okay, all right, so I want to do an example. I want to do an example of how engineers might go about attacking a problem in this cost of goods manufactured. It's 14 examples, so I might have to skip a few, but I'll leave them in my notes and then you can look through them at your leisure. Here's where the story begins. This is that shunt problem that I told you about right before. This shunt problem is now assigned to test sort. So right now the testing and sorting team is feeling the pain and suffering, okay? It's 0.5%. It's end of line yield, so we've already loaded these wafers up fully with all the cost. So throwing them away is painful. We're throwing away all that $27.41 every day in my little mini simulation. It's about 0.5% yield. It's adding about 1/4 cent per watt to our cost of goods manufactured. If we could capture it, in our little 800 megawatt factory, we would get around $8 million return. Okay, so it's a big number. It's assigned to the yield engineering team, so they are feeling the pain and suffering. They're actively working to understand why is it that we have a shunt problem. Why do we have a shunt problem? They're trying to find the root cause of the problem. What they want to do is they want to find out which process step is causing the problem, right? That's what they're trying to do. And they find evidence, and what they find is this. This is our story. They discover the root cause. So in our little simulation here, we're making selective emitter solar cells. And we make this one diffusion here with some screen printed paste, and then we print on top of it with the metal. And they have to be lined up. Okay. What's happening is, due to just normal common cause variation in the processes, what's happening is sometimes this particular pattern is offset. It's called pattern offset. And when it gets offset, then we have the metal here touching the wrong part of the solar cell, the lightly diffused side. And that causes the shunt. That's where it comes from. It causes the shunt path, and it's also responsible for that local thermal anomaly that our customers are complaining about. Okay, so that's good. So the yield and test engineers have discovered the root cause. The root cause is it's happening at this process step here. This, I call it P print. I don't know, P dopant print. So the first thing they do right away, step one, is we reapportion the cost. We reapportion the cost. It used to all go to test sort. We reapportion it to P print now. So now the P print team is responsible for these costs. Okay? The root cause is not at the test sort process. It's in the P print process. And so step one is we want to apportion all the costs as close as possible to the point of the root cause. We want to put the cost right on the root cause. Okay? We want the people closest to the root cause of the problem to feel the pain and suffering. And that's P print. So now they feel the pain and suffering every day. You guys are off the hook. You're sleeping like babies. No more need to be at work at 8 o'clock to present to ops. No more need to have a detailed analysis every day of what you've done and what you're going to do. It's now P-print's problem. So now you guys are getting called up every morning at 4 a.m. You got to come to the factory. You got to stay late at night working. Okay? You're the ones doing all the updates at the operations meetings 2 times a day. You're working your backside off. Okay, that's good because you know why that's good? It's because the test guys cannot fix the problem. They don't know anything about print. They know about how to calibrate. They know how to check the voltage and make sure it's on track. They know all about testing and sorting. They know nothing about printing. They can't do anything about the root cause even if they wanted to, which they don't. So you guys are the ones that can do something about it. So that's why we want you to feel all that pain and suffering, so you will be highly motivated to apply your skills to fix the problem. Okay, so that's the first thing we do. The second thing we do is now what we do is we start monitoring the problem as close as possible to the root cause. Okay? Before we were monitoring the problem at test sort, right? We had a measurement of shunt. That's how we monitored it. Okay? The problem with that is it's too little too late. By the time we measure it, it's already 2 days later. Right? The problem has come and gone. It's too far away. And we don't have any immediate feedback when there's a problem. So we do it now. We do it at the printing step. We sample this pattern offset. We hire a technician every 10 minutes. He gets a wafer, he looks on the microscope, and he measures it. We do this at every shift, every day, on every tool. We start measuring it at the source of the root cause. And we can get a little chart like this, and we start to keep track of the charts. Everyone's looking at the charts, and we develop a criteria, which is anytime pattern offset is greater than 20 microns or less than 20 microns, we fail it. We fail that wafer. And we do something. We have an action plan. We fail the wafer. We stop everything. We call the engineers immediately. And they rush inside immediately and start to look what happened, why did it happen, where did it happen? Did you notice anything that happened interesting, different? You know, and we do an immediate observation at the tool at the time that it happened. Okay? We don't wait around until it gets to test sort in the middle of the night and then we wake up the next morning. We go there the minute it happens, even if we have to wake up in the middle of the night to do it. And then the other thing we do is we reject everything that's out of spec. We reject it. No point in continuing to dump cost into this wafer, because if we're just going to throw it away later, then we're just wasting our money. So we throw them away. There's a big pile of wafers by your tool now. It's getting bigger and bigger every day. It's an embarrassment. You guys are embarrassed about it. And when the fab director walks through and he sees that pile of wafers, you're embarrassed because you just know that's just wasted silicon and materials. And he says, okay, guys, I know you're working hard. Keep working faster if you can. We got to get this pile taken care of. Okay, good. That's the pain and suffering factor. Okay, so we could try to recalibrate the tool offset, right? We can see, look here. This is the average, this dotted red line, and this is the target here, the blue line. We can recalibrate, but we apply our statistical tools like this. We do a t-test concerning the average. I don't know, there's some numbers here. It's a simple calculation. But what we do is we fail to reject. We don't see any evidence that there's a problem with pattern offset. Okay, so the problem is not related to tool offset calibration. We're trying to, I should frame this up. We're trying to contain the problem now, right? We're trying to contain the problem at the source of the root cause. We don't want to contain it at the customer. We don't want to contain it in the field. We want to contain it right where it's happening. OK, no opportunity here. We look at, oops, wrong way. We look at the standard deviation. The standard deviation is a problem. There's a lot of variation in this tool. What we do is perform a full tool maintenance because we think, you know, it must be the maintenance. First thing we always check. Shut the tool down. We check everything. We grease everything. We do everything on the full tool maintenance schedule. And then we start it up again, and we get the new data, and we say, all right, did the standard deviation go down at all? We don't know. But we can use an F-test, statistical F-test. More numbers here, which you have to love statistical hypothesis tests to know what these mean. But the conclusion is no evidence that there's any improvement in standard deviation. All right, so the two easy things that we thought to try, you know, the normal standard calibration and the normal standard maintenance, no luck, no improvement. OK, we're still suffering. All right, we're going to contain the problem using a methodology called design for capability. We're going to design the process so that it's capable. In other words, so that it has low yield. So what we do is, right now the capability is 0.92, and that's what results in 0.5% yield loss. That's a pretty low number for capability. So we take a model of all the data. We build a population model. It's just a statistical regression model. We collect the model parameters, mean, standard deviation. And this is our fail criteria, if you remember from that chart from before. And we say, what would it take to reach a CPK of 1.5? That would be a very, very low yield number. And what we do is we change the specification. So basically, we just move the failure bars. We move them out. We say, all right, easy. We just move them out to here. And then nothing will fail. It's perfect. All right, how do we do that? Well, what we're going to do is we're going to change the mask design. We're going to change the mask design that we use to print the pattern. And we're just going to make this little buffer width here. This is the area where we have the failures. Remember from my big picture from before? We'll just make this wider. You know, we'll make the target bigger so we can't miss. So we make it wider. And it's easy to do. We can do a calculation. We can do a design for capability calculation to get some numbers here, calculations. Before we were at 40. We know if we increase it to 67 or 68, then we will reach a CPK of 1.5. And that results in a yield loss of 7 defective parts per million, which is pretty good. Solves the problem. OK, so we just changed the rules. We go back to our CAD drawing, and we make everything bigger. We can't miss now. It's perfect. OK, and this is what our cost of yield looks like. As we change the buffer width, we can model that. And then this is where we are now. This is where we are if we change the design rule. Except there's a catch here. There's a catch. There's a little catch to this picture. The R&D guys are not happy about this because they worked so hard to get the efficiency up. And now you're going to make this bigger. It's going to increase their J0. So they're a little unhappy. They don't want you to do that. They want you to keep it narrow. So you're going to give up a little bit of efficiency. And the accounting guys, the procurement guys are a little unhappy too, because now it's going to cost a little more in terms of the dope and pastes. We're going to use more dope and pastes. So that's going to have an impact on our cost. We're going to lose some efficiency, and we're going to lose some costs. So what we can do next is we can go back to the problem, and we can do a design for cost methodology. So now we understand cost, because we learned our cost accounting, and we're all really good at device physics, so we can predict exactly how much efficiency we're going to give up. And we can make a new model, which is the cost of lost efficiency and extra dope and paste, like this orange one. And then we can combine the two costs together in a relatively simple model that predicts the optimum pitch or the optimum buffer width by cost. And that's something like right in between here, like this. So we find the lowest net cost. And that's our containment solution. Containment solution, we deploy that across the factory, and then we check, we validate to see the results. And here's what happens. We got most of it. We got the yield loss down to 500 EPPM from 5,500. We also improved the cost of poor quality, since these things have the same root cause. So that fixed a bunch of problems. However, we gave up a bit of efficiency, and we gave up a bit of usage rate of our dope and paste. So it was a bit of a compromise. It's containment only, though. This is what we in manufacturing call containment. It's not a corrective action because it doesn't address the root cause of the problem. It only addresses the symptom. And we really didn't get as much as we think we can get. So we're not done yet. We're not done yet as engineers. I might be out of time, but as engineers, we're not finished. We have more work to do. We do a benchmarking. We look at all the printers in the factory. This is our P print tool, the one that's giving us so much trouble. And this is the F print tool. This is the one that does the front metallization. Look at that. It's super different, right? Look at this low standard deviation. We're all drooling. Print team, we're drooling over this. This is like, how do we get this? Significantly better. We believe we could do this in our tools as well. We do an F test. We check, are these standard deviations the same? We reject the null hypothesis. Yes, we conclude they're different. So now we have something to go on. Why are they different? Why are we worse? Why are we worse? We do our 5 whys. Why are we worse? And you say, well, we have a new model of the tool. It's lower cost model. And then I say, well, why does that matter? And then you say, well, it's got cheap components. And then I say, well, why are the cheap components not working? And you go on and on and on like that until you either keel over or you figure out what's wrong. But in conclusion, we realize so many things that are different. Could be anything. We don't know. Could be anything. OK. Now we need to figure out which factor is the root cause. OK. We have many possibilities. We brainstorm. The list is very long, but we can kind of prioritize this a little bit. It's too many. It's too many for us to analyze in a short period of time. OK. Now we bring in our design of experiment skills, right? We create a multi-factor factorial experiment. We pick 5. We do a 5-factor. We do a half fractional. And we use statistical analysis of variance, which is going to tell us about the variance under all the different possible factors. Here's what it looks like. It's a cool picture, I think. This is the hypercube of a 5-factor half fractional design experiments with 16 legs. We collect all this data. We put it through our Anova analysis. You guys are not going to make heads or tails of this. Just remember that I said it's pretty cool when you work it out. We look at all these p-values, and they all indicate no influence of any factors. Nothing has any influence on the variance of all the things we tried. None of the main factors, none of the interactions between factors, nothing. So basically, we've come up empty-handed. Nothing has worked. We've been suffering for now. We're into month 4 of pain and suffering, and we're getting to be really, in our hearts, very sad. All right, so what we do is the R&D guys say, let's take another tact. Let's develop a process that's fault tolerant. Let's change the times and the temperatures and the concentrations and other things like that so that when the process fails according to our pattern offset, it won't kill the solar cell. OK, that sounds like a good idea because we're kind of at our wits' end when it comes to the variability. So now we do the same thing. We brainstorm. Oh, there are many factors. It's going to be a lot of work. But we design another screening DOE. We design another design of experiments. We do a screening DOE. We sort out which one of these are important. Then we do an RSM DOE to build a regression model, a statistical regression model, which we use to predict the best recipe. That's the plan. So we're halfway down this path, and then a miracle happens. A miracle happens. The operator calls you up at 4 a.m. and he says, you got to see this. Come in here. You're not going to believe it. You go in to the factory, and here's your printer. It's running good, just as we expected. It's running bad, but nothing new. He grabs onto the machine, and he starts shaking the machine like this. And all of a sudden, the variation in the pattern offset goes through the roof. You know, it's going like this. And then all of a sudden, it's going like this. And you're like, that's the factor. Don't shake the machine. Easy. OK. No, not really. You look at it, and you look at it, and you realize when the operator's shaking the machine, it's shaking the camera. The camera's wobbling, and the camera's the thing that looks at the wafer and decides where the pattern should be. And so it's seeing this, you know, and that's what's adding all the variance. So we found the root cause. When the printer's running, you got all these parts moving, right? And that creates an impulse on the frame of the tool, which shakes it and makes the camera shake. Confuses the software. And as soon as you realize that, you're on the course of corrective action. Within a day, you've got it all sorted out. You know, isolation mounting, optical reference points, you're done. You make that fix in your process, and what do I do with my pointer? Here. And all of a sudden your variation goes down. It's starting to look a lot like all the other tools, and now you do another F-test. You do an F-test, you find no evidence of any difference between these two standard deviations. You're good. You've found the problem, and you've found a good corrective action. You go and you validate the corrective action. It's all looking good. There are no more yield losses due to shunting. There are no more local thermal anomalies. You found the root cause. You found the corrective action. And the print team is happy, and they return to a normal life. Except, no, they're not done yet. Not done yet. There's more to do. This is now what you have here is called excess capability. So your CPK is now up to 6 with those design rules. And excess capability equals money in a factory. If you have excess capability, you have some opportunity to get more money out of your process. You can lower your targets down. So like, let's say this is the target for etching of silicon, of sodium hydroxide etching. You want to etch this much. You can lower this down and you can etch less silicon. You save on money of cost of sodium hydroxide. You can change your spec limits too. That's another thing you can do, shrink them down. And that's precisely what we're going to do. We're going to go back and make the buffer width smaller. We're going to redo our cost of design, design for cost. These are the new ones here, the dotted ones. So we get a new local minimum that's better than anything we've had before. And we get the low yield loss. We get the efficiency back. And we get lower dope and paste usage. So it's a win-win-win for everyone. And everybody's quite happy. And you guys, the print engineering team, being awesome engineers that you are quite successful. Finally, we've reached nirvana, almost. There's one more thing to do. Now I want to see if anyone can get the last thing we do. Anyone know? Anyone want to guess?
Big fat report.
Big report. Nope. Not if you have to. Not if you don't have to. But good guess. Write a paper. Not allowed. Last thing. There's more money to be made here, even in nirvana. We get rid of the chart. We throw it away. Why? Because it costs us money to make the chart. And the chart doesn't add any value to the product. The customer doesn't care about a pretty chart. He just cares about watts and numbers and yield. So we throw it away, and that's the last thing we do to get rid of the chart. OK, at the end, we saved half a cent, fictitious half a cent on our 800 megawatt capacity. It was a $14 million NPV over 5 years. We had some project costs, line time, materials, labor, blah, blah, blah. Total of $700,000. We had an ROI here on this little project. It's 26.8. So it's a good return. All right, so this example was fictitious. All the numbers, I made them up. But what I wanted you guys to see, I wanted you guys to see a little bit about the methodology that we follow in manufacturing to tackle factory cost. Right? It's a robust methodology, engineering methodology that you can follow. And there's a lot of skills that you need in order to be able to practice this methodology. You need to know your hypothesis testing, your design of experiments. You need to know your cost. You need to know how to analyze Anova. There's a whole bunch of things you need to know in order to make any sensible progress in the chaos of a factory. OK, now, this brings me to my last topic, which I'll go pretty quickly. Because I feel so strongly about this, I'm working in collaboration with NU and ASU to develop a course that teaches these basic skills, a manufacturing science of solar cells course. So when I say manufacturing science, I mean hypothesis testing, cost analysis, I mean design of experiments, regression models, I mean chart models and population models. That's the kind of thing I'm talking about. You engineers need to know these things to make a contribution to the factory cost. OK, so this is my course. I'm going to tell you a little bit about it. It's the virtual cell fab project. I got a lot of really good collaborators going right now. And we're talking here at UNSW. I hope we can add them here to my list of collaborators. It's a course and a set of materials that lecturers at all universities can use in order to teach in the area of manufacturing science. So here's a rough curriculum. DOE, regression modeling, chart modeling, population cost accounting, SPC, metrology, design principles, Anova, things like that. And the thing that's the centerpiece that I think is pretty cool about it is we have a simulation software package that the students use in order to do all their work. So this is like our laboratory simulation. And the idea is that it captures a lot of the context of a manufacturing environment. It captures the chaos. It captures the pressure on making output. It captures all of the variation, a whole bunch of stuff that's the context of manufacturing, and brings it into a simulation. It does a really bad job at modeling the physics and chemistry, and I often get people who ask me if they could use my software to simulate their cell fab process, and I tell them no, because this is all made up physics. It's all just made up physics. It kind of looks right, but it's not really very accurate. The thing it focuses on is all the costing, the statistics, the operations variation that you see in a manufacturing environment. And the point is to support teaching and learning in the area of manufacturing science. So here's what it looks like. In the cloud, we have a virtual factory that runs on the World Wide Web. And that ticks over every hour. It makes a few more solar cells and kind of pushes things through the factory. And then we have the client interface, which is the virtual manufacturing execution system. So I've modeled it after an MES. And MES is what manufacturers use to control their factory for all their engineering work and all their operations work, to control all the tools, to schedule maintenance, and everything is done through a manufacturing execution system. So we've kind of mimicked that there. And the students use that as their portal to the factory. And then we have, here they are doing their labs, and then we have a bunch of supporting material that we use in order to practice and learn about working in a factory. Here's what it looks like. You can see that each tools, there's 6 production lines here. They go this way. Each one of those blocks is a tool. And you've got, like you can do engineering lots here, split lots if you want. You've got tool inventory and status. There's a whole cost accounting model built into the whole thing. You can plan out your engineering activities if you want to, for example, work on fixing some yield problem here, or maybe you want to work on getting the throughput up. You got line metrics, a whole bunch of line metrics, and then, of course, end-of-line query and data collection, which you do. Basically, you create your engineering lots, and then when they get finished their production, you query the data, and then you do your analysis and develop your conclusions. And then here's the compelling context that I've built into it and to keep the students interested and engaged. This here is the cash flow, and this is the cash in the bank. So the students start out with 40 grand. And we have several teams going, and each team is responsible for one production line. So they kind of compete. They start out with 40 grand, and of course I've set the whole thing up in advance so that they're losing money. So they're losing money, losing money, losing money. This blue one is the unattended line. We don't have anybody attending this one. So this is the train wreck that's waiting to happen. And so they struggle and try to work on activities that improve their cost of goods manufacturing. We do hypothesis studies, we do regression models, we do designs of experiments, all inside this virtual environment. And everything they do takes a little bit of a piece out of their cost of goods manufactured. And slowly, 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 they start to turn the ship around. It's hard to say right now, but some of the teams are actually starting to make a profit now. And then it's a race to the finish line to see who can make the most profit by the end of the year. So I put this to the students at the beginning of the class. I say, after 1 or 2 days, I say, can you fix the company? I'm going to teach you how, but can you do it? And so they try to save the virtual solar cells throughout the year. And that's all I have. Thank you very much for your warm and kind attention. I'd love to take any questions you might have. Hi, Sabrina. Yes?
Hi, Jeff. Thanks for the talk. It's very interesting. I've got 2 questions. The first one is regarding the platform development phases. You talk about 3 different phases. One is the new platform development. The other one is platform improvement, and the last one is COGM improvement. Of course, I understand that most of the work in the industry is focused on COGM improvement. But I'm just curious that how much of the research and development is actually focusing on platform improvement, or is there any that is trying to develop new platform?
Yes, there are. I mean, most PV companies, or maybe not so much these days, but let's go back in time 5 years. most PV companies had development activities in all three of those areas. So I think Q-cells is a good example. So Q-cells had development work in cell architectures, so different ways of making silicon solar cells. They had the Quebec cell structure, which was a rear side contact cell. So that would be a improvement, platform improvement. They also working in thin films as well. So they had, I believe, CD, CAD-TEL, and CIGS, and crystalline silicon. So that would be a new platform development.
So I got another question regarding the cost validation. When things don't really go according to plan, you guys do projections and predictions and all sorts of things. So I'm just curious, is there a point in time where you decide that this is the limit, it's the cheapest it can go? And when that happens, what do you do about it?
You stop working on cost of goods manufactured improvements when you reach the point of dwindling financial return. So you keep working on it until that NPV, that 5-year NPV, gets to be below a certain ROI that's defined by the company. So you might have a limit on your ROI of 5. The finance team in the company would say, we're not going to give out any project funds for any projects below 5 ROI. 5 might be 1,000% or something like that, right? And you keep working on it until you run out of those, and then you stop. Unless something new comes up, some new opportunity comes to your attention, then you might start working on that. Yeah?
If you're on a production line that's really large and everyone's really specialised in their area, you can see it'd be a problem if you have an interaction between two tools and two teams that takes an overview to see that problem. Do you have people that work on that level across tools?
Yeah, usually it's the responsibility of the integration engineering team. So these are very seasoned, very expert manufacturing engineers who've worked at many of the process steps throughout their career. And then they get a position on the integration engineering team, and they help coordinate processes where you have interactions. You work very hard, though, to remove those interactions. In ideal manufacturing, every process is a unit process and has no interactions with any of the other processes. Right? So no, like, I don't know, a good classic example is the properties of your arc film affect the way you fire through at print fire, right? That's an inter-tool interaction. You try to get rid of those if you can. And if you can't, then it's the integration engineering team responsibility to know about both of those and then work with both teams together in collaboration and guide them to finding whatever it is they're looking for. I saw another hand go up over on here. Did someone have a question? Yeah, John.
Jeff, a lot of the statistical analysis that you do in this development work, in this troubleshooting work, often relies on you having nice, uniformly distributed metrics, the things you're trying to measure, whereas that's not always the case. You know, when your maintenance team decides to do a bit of preventative maintenance in the middle of your test or before and after.
That never happens. That never happens.
In your experience, how much time do you need to spend trying to get that test bed platform right before you can actually effectively conduct these experiments?
There are a lot of, and I didn't talk about any of these, there are a lot of techniques for good experimentation, methods, like randomization is the classic one. Randomize your run orders. Stratify your results if you have to. Like if wafer resistivity is a big factor and you can only get wafers of a variety of resistivities, you stratify that. You just work with certain ranges. Homogenization is another. So another one that's a really big one too is, you know, a lot of experiments in the factory get broken because of some kind of a mistake that gets made. You know, like I used to have a problem where some of my R&D lots would go missing. They would get mixed up with normal production, end up getting sold to the customers. Of course, the customers don't know, but for me it's so painful because now I have a perfect 16-leg design of experiment with 3 missing legs. And so that just stuffs things up. So you have to, in addition to knowing the statistical analysis, yeah, you have to be very savvy at experimental methods as well. And what I always emphasize is planning. I always emphasize experiment planning. Spend more time in the planning phases. Spend a lot of time with the operators who are going to run your experiments. Make sure they understand exactly what it is that make sure they understand why you're doing the experiments. So they care about what happens the same way you do, right? And so that's a whole nother topic we could talk about for another hour on how you do experiment methodologies in a factory. Yeah. Matt.
How do you prevent all the problems being blamed on the print line?
You know what? That's what happens though. It's always the printer. You were in print, right? You were working in print.
Because I was the print
Were you
engineer.
were you in pain and suffering?
Oh yeah, yeah.
Do you know what I mean? Does Matt know what I mean? You know what I mean.
I was getting called up at 4 a.m. every night.
Me too, man.
And then I'd come and find the wafers were half as thick as they were supposed to be, for example.
Yeah.
So they're all being overfired.
That's
or,
right.
Or there's
Yeah,
no
yeah.
text. The texturing's not working all of a sudden, but they assume that it's a...
Well, that's what happens. That's what happens. Yeah. Okay. So there's a problem in print. Now the whole factory is aware of it. Everything that's a problem is a print problem, whether it is or it isn't.
Yep.
You got to sort it out, man. That's where you got to have a good, strong yield team. It's the yield team's responsibility to kind of steer that assignment, right? They have to be able to take apart every problem and deduce what's wrong with it accurately. And if they get it wrong, then what happens is the print team starts getting the thickness problems at the wafers when it should be a procurement problem, right? And there's nothing you can do about it. And you can talk until you're blue in the face about how it's somebody else's problem, but it's too late, the blame, it's already stuck. So you got to have a good, strong yield team. They have to get the root cause right. Otherwise, you're just going to waste a lot of pain and suffering and effort working on the wrong people working on the problems. And that's part of the art of doing it in manufacturing. That's part of the art of being a good manager in manufacturing, is steering that assignment of the root cause the correct way. If you can do that right, then the rest of the factory will respond in a way that gets the job done. It's kind of almost organic, it's like a amoeba, if you get the RNA channels right, it lives and breathes. We should have a little beer and commiserate later.
You can do it in front of us.
Oh yeah, okay, good. I did work in print for a long time. I spent a lot of time in print, yeah.
So given all the problems that always due to screen printing, maybe we should move on from screen printing. But anyhow.
Oh, I hate to tell you this, but I had even worse problems in inkjet. Oh my God. Okay, question.
So what was more rewarding, chasing electrons around the solar cell in the lab, or chasing dollars around the manufacturing lab? For you. It was the most rewarding thing for me was being very low on the learning curve in manufacturing, and feeling like I was learning a lot. And I still love both topics. And one of the things I do now in my consultancy is review grant applications, and I love doing that because I love reading about all the physics and cool stuff that's going on. But what I see is I see lots and lots and lots of programs, educational programs, training engineers in the physics, the process chemistry, and nobody working in the manufacturing science. And so I feel compelled to get that into everyone's awareness, get it into their programs, so that we have more engineers who can function in a manufacturing environment better, faster, with less pain and suffering, less cost. Torsten.
Now you've worked at SunPower, which of course is probably the company which is most advanced when it comes to this very systematic analysis. Can you comment on your views on how these sort of things are tackled in production lines in China?
Don't know. I don't know. But I know there are other companies that are equally sophisticated to SunPower that I know are just as good. But I haven't been to any factories in China, and I don't have much interaction about how things are done in China, so I just don't know.
So kind of follow on from that, which industry did this kind of come from, do you think? Like, do you have any insight?
Good question. Hypothesis testing comes from the beer industry, believe it or not. The t-test comes from the beer making, brewmeisters. It was a brewmeister who invented the tea statistic, the tea tables. a lot of it comes from, a lot of the methods come from semicon. Semicon is very sophisticated. Automotive is very sophisticated. Like automotive is very sophisticated in Six Sigma methodologies, which a lot of Six Sigma, the underpinning is the same as what I've shown you. In electronic assembly, it's a lot of lean principles. They use a lot of lean principles. And, but still, again, a lot of the same things apply, right? You still use a lot of statistical underpinnings. So I guess in PV, you know, it comes from the long, long history of everything and anything, wherever anyone has, where did the statistical process control charts come from? I forget. Westinghouse. Westinghouse, right? There is a completely different industry for you. Invented the SPC charts. I think it's Westinghouse. My history is not very good. So it comes from bits and pieces from everywhere. And anytime you can find something that works, you use it shamelessly. Yeah, good question. Yeah. Oh, sorry. Any other questions?
Yeah, we probably should wrap up. So we're going down to, it's time to try to take Jeff out of the room. Jeff is more than welcome to. But I'd like to thank Jeff for coming and talking to us today.
It's been my pleasure. It's been my pleasure.
Just for your information, what we're trying to convince Jeff to do is come back to UNSW, not this summer, but next summer, and to run his manufacturing science course at UNSW as a short course over the summer. So it will tail on from the manufacturing course that we teach here. So we'll need some teaching assistants to help us run that course. So if you're enthused, then keep that in mind. So anyhow, thank you very much, Jeff.
Thank you.